right, so nitriles, we see we can hydrolyze them. When they're hydrolyzed, they stay in the same oxidation state. How do we change oxidation states? We either oxidize or reduce molecules. And the nitrile is already pretty much in the most oxidized state that it can be in. So what can we do to it? We can reduce it. So we can decrease its oxidation number from 3 to something lower than 3. Hopefully you guys can fill in this box. The strongest reducing agent for polarized functional groups was blank. Think back to that. We did a lot of that in chapter 20. It was lithium aluminum hydride. And what did lithium aluminum hydride do when we reacted it with an amide? It turned that amide into the amine. So it turns out that we can also reduce nitriles with this super strong reducing agent, lithium aluminum hydride. And the nitrile is going to be fully reduced. I mentioned back then lithium aluminum hydride will fully reduce all polarized functional groups. So we can reduce the nitrile fully to the amine. So lithium aluminum hydride, we're going to use that. And remember, lithium aluminum hydride is super reactive as a hydride reagent. It can't be in the presence of acidic protons, so we have to use some polar aprotic solvent like diethyl ether in this reaction. So that would essentially do something like this, where we say that this is kind of H-esque. But really, like how that works out is that the aluminum hydride, the hydride takes those electrons and adds them, so it's the negative flowing to the partial positive on the carbon of the nitrile. And at that point, these electrons are going to have to come up to the nitrogen, but what they're going to do is essentially coordinate to the aluminum. Remember, the aluminum, if this hydride leaves, has that empty p orbital. So essentially, that one time would produce something that looked like this. So we'll put the hydride down there, nitrogen up there with AlH3 minus. But then more of these hydride equivalents can add to that position, and essentially more hydrides would add in. So another version of this, we'd add another one in. We'll essentially make the product look like this, where we have 2 equivalents of the hydrogen added there. We'll have the AlH3s attached to the nitrogen. So then how does this complex break down? Essentially, we're going to add water as part of the workup step, and that water will add to the aluminum. So essentially, when we add reagent 1, it gets it fully reduced, and then 2 removes those aluminums from the nitrogen, fully reducing that functional group to the amine. It's hard to, that's a 2 right there. So that's what lithium aluminum hydride can do. We can fully reduce that nitrile to the amine. What was the most mild reducing agent for polarized functional groups? Yeah, so lithium aluminum hydride had a more polarized aluminum hydride bond compared to the less reactive reducing agent, and that one was sodium borohydride. And essentially, if we were to take sodium borohydride, react that with an amide or an ester or carboxylic acid, it's essentially not strong enough of a reducing agent to do anything with those. Turns out that nitriles are also not reactive enough to react with the less reactive hydride reagent. So it produces no reaction with nitriles. There was another reagent we learned about for partial reductions. Turns out that's also going to work with nitriles. We'll talk about that in a minute. Okay, so we had our strong reducing agent, lithium aluminum hydride. We had our weak reducing agent, sodium borohydride, and the kind of middle of the road, not too hot, not too cold, reducing agent that we learned about previously was dibal H. dibyl H. And the moderate reducing agent dibyl H, it turns out, can partially reduce nitriles in the same way that it partially reduced esters to the aldehyde. So if you recall, chapter 20, we learned that if we treat an ester with dibyl H, which again is diisobutyl aluminum hydride. So that's an aluminum with a hydrogen, and then two of these isobutyl groups. So I'll just put a 2 there to show that there are 2 of those there. This is also kind of a hotter reducing agent, so we have to use an aprotic solvent. So we'll put that in diethyl ether. And then secondly, one other consideration for dibyl H was essentially we had to use it at low temperature. And then we worked up the reaction with water, just like we did with lithium aluminum hydride, and that got rid of the aluminum, freed up the product to be neutral and go to the organic layer in an extraction. So it turns out we can do a really similar thing with nitriles. We can start out with our dibyl H. We'll put our polar aprotic solvent in there and low temp. And it's going to do pretty much the same thing. So what was that? Well, in dibyl H, what we saw happen previously was we had our aluminum hydride, and essentially this aluminum is not negatively charged, so it's actually more electrophilic than it is nucleophilic, so it requires something to add to it before it's really able to give up the electrons from that aluminum hydride bond to add to the other side. But essentially, that's what occurs. I'm going to add a third arrow here showing that as that hydride goes there, the electrons that made this nitrogen-aluminum bond could have come from the lone pair on that nitrogen. They also could have come from the pi bond, because those pi bond electrons partially belong to that nitrogen, right? So those things would happen. We would have an intermediate structure that looks like this, where we'd have the nitrogen-aluminum bond. And what we said when we talked about this last time was that essentially these isobutyl groups make this nitrogen so sterically hindered that it is not possible for any extra equivalence of this dibyl H to further reduce it because of those big arm-like isobutyl groups. So this complex was stable at low temp, and then we essentially would take that at low temperature, and what that looks like is that it's essentially in a dry ice bath, so it's at minus 78 degrees Celsius, and we would add water to that. The water would pull that aluminum off essentially, and then it would also add here. We have an imine here. This is an imine, and what did imines come from back in chapter 21? Imines were formed from the aldehyde reacting with a primary amine. How did we get rid of imines? We added a lot of water. And essentially, if you want to look back at that chapter for this mechanism, if we add water to this, so this is kind of part 2, part 1 is forming this complex, reagent 2, the water, is going to add to this carbonyl, or this imine carbon, and that would be an equilibrium reaction when we have an excess of the water. It would push the equilibrium not to the imine, but to the aldehyde. So essentially, the final product here of a partial nitrile reduction is not an imine. That's kind of like the intermediate in the reaction, because we can't really isolate that species. We have to add water during that workup to get rid of all the aluminum salts. And in that process, if we do add water, it is going to hydrolyze that imine to the aldehyde. If we wanted the imine, we can then just add a lot of the amine, the primary amine, to that in a subsequent reaction to form that imine. But what is going to happen here is we are going to have the aldehyde as the final product. So that is all the ways that we can reduce these nitriles. We can do a really strong reductant like lithium aluminum hydride, and that will go all the way to the amine, or we can partially reduce with dival H, and that will stop at the imine, which upon workup, adding our water, it is going to hydrolyze that imine back to the aldehyde. Great.